The far side of the moon is a place humans spent all of history never seeing. For billions of years, it faced away. Then a spacecraft landed there, drilled into ancient rock, and pulled up something that had no business being on a surface. Material from deep inside the moon. Rock from a layer scientists thought was permanently buried. We will visit the deepest crater in the solar system, stand over hidden tunnels wide enough to hold cities, and hear radio signals that reach back before the first stars ever lit up. If you enjoy the journey, a like and subscribe keeps us going. Prepare yourselves. We begin. For all of human history, one half of the moon was simply gone. Every civilization that ever looked up saw the same face, the same craters, the same dark patches, the same familiar shape hanging in the night sky. Ancient astronomers mapped it, artists painted it, scientists studied it for centuries, and the entire time, an entire hemisphere was turned away, silent, unseen. Nobody had ever seen the far side from the ground, and for a long time nobody could. The moon orbits Earth, but it also rotates on its own axis. Here is the strange part. Those two motions happen at exactly the same speed. One full orbit around Earth takes the same amount of time as one full rotation on its axis. The result is a perfect lock. The moon spins at precisely the rate needed to keep one face pointing at us forever. This is called tidal lock, and it happens because of gravity. Early in the moon's history, Earth's gravitational pull created a slight bulge in the moon's shape, like squeezing a softball from one side. That bulge acted as a handle. Gravity grabbed it and gradually slowed the moon's spin until the rotation matched the orbit exactly. Then it froze. Scientists confirmed this process across dozens of moons in our solar system. It is one of the most reliable outcomes of long-term gravitational interaction. So for billions of years, the far side faced deep space. Cosmic radiation hit it unfiltered. Billions of impacts carved into it with no atmosphere to slow anything down. And Earth sat completely unaware. Humans finally got their first look in 1959, when a Soviet spacecraft swung around the moon and sent back grainy photographs. The images were blurry, low resolution, almost unreadable, but they showed something unexpected. The far side looked completely different. Fewer dark plains, more craters, a rougher, older surface that seemed to belong to a different world entirely. That discovery raised a question nobody could answer. Why were the two sides so different? They formed from the same event, out of the same material, around the same time. The near side had vast, smooth plains of ancient lava. The far side had almost none. The crust on the far side was measurably thicker. The chemistry was different. And here is where the story gets strange. Scientists built models, ran simulations, proposed explanations. Some held up, many did not. Decades passed. Satellites orbited and mapped. Telescopes stared and measured. And the gap between the two hemispheres kept resisting every clean explanation. Then, in January of 2019, something changed. A Chinese spacecraft called Chang'e 4 descended through complete communication silence, because you cannot talk to Earth from a place that faces away from it, and touched down inside the Von Karman crater on the far side of the moon. For the first time in history, a human-built machine was sitting on the surface that nobody had ever stood on, never photographed up close, never touched. The rover rolled out. It pointed its instruments at the ground, and within weeks, it found something in the soil that upended the leading theories about how the moon formed and what lives inside it. We will get to that discovery. But first, you need to understand the place where it happened. The Von Karman crater is enormous, roughly 110 miles across, a circle of ancient rock, wide enough that standing on one edge, the other side would sit below your horizon. And it sits inside something even bigger, something that holds a record no other object in the solar system has broken. What comes next will change the way you picture the moon entirely. Picture the largest thing that has ever hit the moon. Whatever you imagined, make it bigger. The impact that formed the South Pole Aitken Basin struck so hard and so deep that it carved a hole roughly 1,600 miles across and about 5 miles deep into the lunar surface. 5 miles down, an object falling from one rim to the floor would take minutes to land. Laid across the United States, this basin would stretch from New York to Denver and still have room left over. Scientists confirmed through orbital measurements that this is the largest and deepest impact crater in the entire solar system, a confirmed record. Nothing discovered so far comes close. The Von Karman crater, where Chang'e 4 landed, sits inside this basin like a bowl inside a bowl. So the spacecraft was already at the bottom of something ancient and enormous, before it even began its work. Now, impacts like the one that formed the South Pole Aitken Basin do something violent to the geology beneath them. When an object large enough hits the surface, it does not just carve a hole, it punches through the crust. It sends shockwaves miles deep into the interior. It can splash material from deep underground up to the surface, like pressing your thumb into wet clay and watching the edges rise. Scientists suspected for decades that the impact forming this basin was powerful enough to excavate material from the lunar mantle. The mantle is the thick layer beneath the crust, a region of dense ancient rock that formed when the moon was still cooling from a molten state. Mantle rock never appears on the surface under normal conditions. The crust sits on top of it like a lid, but a big enough impact could crack that lid, punch through it, drag material upward. If mantle rock was sitting on the surface of the South Pole Aitken Basin, finding it would answer one of the most fundamental questions about the moon's interior. It would tell scientists what the deep interior is actually made of, how the moon differentiated as it cooled, and whether the models built over 50 years of study were accurate. Here is what made the Chang'e 4 findings so striking. The rover's instruments detected minerals associated with the deep interior sitting right on the crater floor. Specifically, a combination of minerals called olivine and pyroxene in concentrations that pointed toward mantle origin. Scientists examining the data published their findings and confirmed this as the most direct evidence yet that the basin impact did exactly what the models predicted. It reached the mantle. But the excitement did not stop there, because the ratios and distribution of those minerals did not match what the standard model predicted perfectly. The olivine was present, but in smaller concentrations than expected. The pyroxene dominated. And that raised a new problem. If the moon's mantle has less olivine than models assumed, then the moon cooled and solidified differently than we thought. The sequence of crystallization inside the ancient lunar magma ocean needs to be revised, which means the timeline of the moon's formation, the pressures and temperatures of its interior, all of it is under fresh scrutiny. One crater floor, one rover, and the foundation of lunar science shifted, and the asymmetry between the two sides of the moon, that mystery only deepened from here. Something thickened the far side crust. Something separated the hemispheres so completely that they tell entirely different stories. And the leading explanation for that separation involves a second collision so ancient it left almost no trace. Almost. Stand on the near side of the moon and you see dark, flat plains stretching for hundreds of miles. Stand on the far side and you see craters on top of craters, rough and pale and ancient. Same moon, same origin, completely different faces. This is called the lunar dichotomy, and it is one of the most debated problems in planetary science. The near side is covered in what scientists call maria. These are vast plains of solidified lava that flooded ancient impact basins billions of years ago. They formed because the crust on the near side is thinner, roughly 25 miles thick in places, and volcanic material had an easier path to the surface. The far side crust is up to 50 miles thick in some regions. Lava pushing up from the interior simply could not break through. So why is the crust thicker on one side? For decades, the leading explanation involved heat, specifically a group of radioactive elements that produce heat as they decay, elements like thorium, uranium, and potassium. On the moon, these elements concentrated heavily on the near side, in a region scientists call the Procellarum KREPE terrane. The abbreviation stands for potassium, rare earth elements, and phosphorus, marking a chemically distinct province on the near side covering roughly 16% of the lunar surface. This concentration of heat-producing elements kept the near side interior warmer and more molten for longer. That warmth thinned the crust over time by keeping the rock below it soft and mobile. The far side, starved of that heat, cooled faster and built up a thicker, harder shell. Confirmed science. Orbital measurements verified the chemical concentrations. The heat difference was real. But here is where the story splits. Scientists could explain the chemical difference. What they struggled to explain was how it got so extreme. Why did nearly all the heat-producing elements end up on one side? That level of asymmetry required something dramatic. Chemistry alone during normal cooling did not produce results this lopsided in any simulation. In 2011, a team proposed an answer that sounded almost impossible at first. They suggested the moon once had a companion, a second, smaller moon, perhaps 1/3 the size of our current moon, formed from the same giant impact that created the moon itself. For tens of millions of years, both moons orbited Earth. Then, slowly, gravitational forces drew them together, and they collided. Slowly, at low speed, more like a mountain pressing into another mountain than an explosion. The smaller moon did not blast the larger one apart. The material accumulated on the far side instead, piling onto the crust like a slow avalanche and thickening it. A low-speed collision adds mass without vaporizing it. The result would be exactly what we see: a thicker, more cratered, chemically distinct far side. This theory remains under active scientific debate. Confirmed as a serious hypothesis, not yet confirmed as fact. But the crater shapes, the rock layer compositions, and the crust thickness measurements all fit the prediction with unsettling accuracy. Here is what makes this idea so significant. If true, it means the moon we see overhead is actually two moons merged into one. Every time you look up at that familiar face, you are seeing the side that survived. The far side carries the scar, and buried inside that scar are anomalies that nobody expected to find. Magnetic signals coming from a world that should have no magnetism left at all. The moon has no global magnetic field today. That is confirmed. Earth's magnetic field comes from its churning liquid iron core. Convection currents moving deep inside generate a field that extends thousands of miles into space and shields life from solar radiation. The moon's core stopped doing that long ago. The interior cooled, the convection slowed, and the field died. Scientists calculate this happened somewhere around 1 to 2 billion years ago. So when spacecraft began mapping the moon's surface in detail and found patches of magnetized rock scattered across it, the discovery created a serious problem. Magnetic rocks form when molten material cools inside a magnetic field. The minerals inside align with the field as they harden, locking the magnetic signature in place, like a fossil. This is how scientists read ancient magnetic fields from rock on Earth all the time. The rock becomes a record of the field that existed when it solidified. On the moon, those magnetized patches exist, and on the far side, they appear in concentrations and orientations that do not match what a simple dying global field would leave behind. Some of the strongest magnetic anomalies on the entire moon cluster on the far side, far away from the obvious volcanic provinces. In places where the surface rock has no clear volcanic or impact origin that would explain fresh magnetization. One leading theory connects these anomalies to large impacts. When a massive object strikes the moon, the impact generates a plasma cloud. That cloud of charged particles can briefly compress and amplify any existing magnetic field at the antipodal point, the spot on the exact opposite side of the moon from the impact. If the surface rock is cooling or disturbed at that moment, it captures a stronger magnetic signal than the background field alone would produce. Several of the strongest magnetic patches on the far side sit at the antipodal positions of major near-side impact basins. The geometry matches. Scientists consider this a strong candidate explanation, confirmed as a correlation, still debated as a mechanism. But a second possibility exists, and it is stranger. Some researchers propose that the moon's magnetic field did not die smoothly and evenly. The interior may have cooled asymmetrically, with different regions of the core solidifying at different times and leaving pockets of sustained magnetic activity in specific areas. If those pockets persisted longer on the far side interior, they could have magnetized surface rock long after the global field officially ended. An asymmetric core, one side still slightly alive while the other had already gone cold. This idea is still theoretical. Models support parts of it. Direct sampling of the far side's deep subsurface, would be needed to test it properly. And that kind of sampling has never been done. But here is why this matters beyond the moon itself. The difference between a planet that keeps its magnetic field and one that loses it is the difference between a planet that stays habitable and one that gets stripped bare by solar radiation. Mars lost its field. Mars lost its atmosphere. Earth kept its field. Earth kept its oceans. Understanding exactly how and why planetary cores cool and what determines whether a field survives is one of the most important open questions in planetary science. The far side of the moon may carry the clearest record of that process anywhere accessible in the solar system. And beneath the surface, something even more useful for humanity's future has been confirmed. Frozen, ancient, and waiting. There are places on the moon that have never seen light. Near the lunar poles, the terrain is rugged and the craters are deep. The moon's axis tilts only slightly compared to Earth's, so the geometry of the craters near the poles creates flaws that the angle of incoming sunlight can never reach. Permanently shadowed regions, scientists call them. Some of these craters at the South Pole have not received a single photon of direct sunlight in billions of years. The temperature inside those craters drops to around -300 degrees Fahrenheit. Colder than the surface of Pluto, colder than anywhere else in the inner solar system. At that temperature, volatile materials do not evaporate. They stay, they accumulate, layer by layer over billions of years. Anything deposited there by passing comets or asteroid impacts gets locked in place and preserved. Scientists confirm the presence of water ice in these permanently shadowed regions through a combination of orbital observations and a deliberate crash. In 2009, a spacecraft intentionally slammed into a shadowed crater near the lunar South Pole, and a following probe flew through the debris plume, analyzing what it kicked up. The instruments detected water vapor and ice. Confirmed. Real water on the moon, preserved in the dark. Further observations from orbiting spacecraft found water ice signals across multiple craters near the South Pole. The ice does not sit as a pure layer. Scientists describe it as mixed into the soil like gravel in concrete, distributed through the top few feet of the surface in varying concentrations. Now here is the piece that connects this directly to the far side. The South Pole is located on the boundary between the near and far sides. The South Pole Aitken Basin, that enormous ancient impact structure discussed earlier, dominates the terrain there. Many of the permanently shadowed craters with confirmed ice sit at the edges of this basin, or inside craters nested within it. The ice did not come from the moon itself. The moon formed hot and dry. Scientists believe comets brought much of it. Comets are essentially dirty snowballs, and when they struck the early moon, their water was released. Most of it escaped to space, but some reached the poles before the sunlight could grab it, and dropped into the permanent shadows where it has sat ever since. Some of it may also have arrived as hydrogen from the solar wind that combined with oxygen in the lunar soil to slowly produce water molecules over millions of years. Both processes likely contributed. Why does this matter so much? Water is the most important resource for long-term human presence, beyond Earth. Carrying water from Earth to the moon costs an enormous amount of fuel. Every pound launched from Earth's surface costs thousands of dollars in rocket energy. Water already on the moon can be used for drinking, for growing food, and for producing rocket fuel by splitting it into hydrogen and oxygen. A permanent lunar base near these ice deposits would have access to the one resource that makes everything else possible. But getting to that ice requires landing near the South Pole, near the far side basin, in terrain that is rugged, shadowed, and difficult. The nations racing back to the moon know exactly what is down there. And one discovery made recently suggests the riches may be even stranger than frozen water. Something warm is sitting beneath the crater floor, and warmth on the moon means something happened far more recently than the models predicted. The moon is supposed to be geologically dead. That has been the scientific consensus for most of modern lunar study. The interior cooled. The volcanic activity ended roughly 3 billion years ago. The surface we see today is a frozen record of ancient violence, untouched since long before complex life appeared on Earth. So when a team analyzing Chang'e 4 data detected an unusual heat signature beneath the floor of the von Karman crater, It forced a very uncomfortable conversation in the planetary science community. Heat flows upward through rock. Deep, ancient radioactive decay in the interior produces a steady, predictable trickle of warmth that gradually escapes through the crust. Scientists can calculate what that background heat flow should look like across different regions of the moon based on rock composition, crust thickness, and the known distribution of radioactive elements. The signal from beneath the von Karman crater exceeded that background prediction. Scientists do not yet have a definitive explanation. Several possibilities exist, and researchers are actively debating which one fits the data best. One explanation involves the local concentration of radioactive material left behind by the ancient impact that formed the South Pole Aitken Basin. The collision could have mixed heat-producing elements from the near side's radioactive province into the far side floor during the impact, concentrating them in pockets beneath the surface. Those pockets would generate more heat than the surrounding rock, creating a localized warm zone. A second explanation is more dramatic. Some researchers suggest the moon may still harbor residual pockets of partially molten rock deep in specific regions, preserved by local chemistry or insulation from surrounding cold rock. The moon's interior cooling was not necessarily uniform. Areas with different compositions cool at different rates. A third, more controversial suggestion involves tidal heating. Earth's gravitational pull constantly flexes the moon very slightly as it orbits. On moons of Jupiter, this tidal flexing generates enough internal heat to drive active volcanism. On our moon, the effect is far weaker, but some scientists argue it could still contribute to localized warmth in specific structural regions. Which explanation is correct? The data from a single landing site cannot settle the question. Scientists need heat flow measurements from multiple locations across the far side to map the pattern properly. The Apollo missions placed heat flow probes on the near side. The far side has never had one. Chang'e 4 carried instruments focused on surface composition, and the heat signal came as a secondary finding from subsurface radar data. Planned future missions aim to address this directly. Multiple agencies have proposed landers carrying dedicated heat flow instruments targeting the far side. Here is why the heat question matters beyond pure science. If the moon still has pockets of geologically active regions, the assumption that its interior is a simple dead cooling ball gets replaced by something more complex. A moon with active internal processes has implications for its long-term stability, for the behavior of its polar ice deposits under different orbital conditions, and for understanding how small rocky bodies age across billions of years. And if geologically active zones exist on our moon, the models used to assess other moons and rocky planets throughout the solar system need recalibration. Beneath the surface, though, a different kind of geological surprise has already been confirmed, one that does not require heat or magnetism to be spectacular. It requires only scale. The tunnels beneath the far side are wide enough to swallow entire city blocks, and they have been there since the moon was young. Billions of years ago, when the moon still had active volcanoes, rivers of molten rock ran across its surface and carved channels through the crust. In some places, the outer surface of those lava flows cooled and hardened first, while the liquid rock inside kept moving. When the flow eventually drained away, it left behind a hollow tube, like a straw buried under the ground. These are called lava tubes, and they exist on Earth too. Hikers explore them in Hawaii and Iceland. On Earth, they reach maybe 100 feet wide. Impressive underground passages with smooth, curved walls and ancient lava marks. On the moon, the lower gravity changes everything. Gravity on the moon is about 1/6 as strong as on Earth. Lava flows behave differently in lower gravity. They spread more thinly, move more slowly, and the tubes they form can grow to extraordinary sizes before the roof collapses. Models predict lunar lava tubes could reach widths of several hundred feet to over half a mile across. The largest theoretical estimates based on gravity data suggest some could be several miles wide. Those are not tunnels. Those are underground cathedrals. Orbital radar data from spacecraft circling the moon detected echoes consistent with large subsurface voids beneath several regions, including parts of the far side. Scientists confirmed the presence of what appear to be intact tube structures in multiple locations, In some areas, the radar signals indicate voids consistent with tubes hundreds of feet wide and potentially miles long. On the far side specifically, Chandur 4's ground-penetrating radar detected what scientists interpret as a possible void structure beneath the surface near the landing site. The data suggested a layered subsurface, with at least one layer showing characteristics consistent with an empty or partially empty space. Analysis of this data is ongoing, and researchers have described the finding as preliminary, but consistent with a lava tube interpretation. One opening into a suspected tube structure appears as a depression near the landing site, a circular pit where the roof may have partially collapsed. Features like this are called skylights, and they appear in multiple locations across the lunar surface in orbital imagery. Why does this matter practically? Underground tubes offer something the lunar surface desperately lacks: protection. The surface of the moon is exposed to cosmic radiation, solar particle events, and micrometeorite impacts constantly. There is no atmosphere to absorb any of it. Long-term human presence on the surface would require heavy shielding against radiation exposure. A lava tube roof of solid rock, even a thin one, provides natural shielding equivalent to far more engineering effort on the surface. A tube wide enough to hold a city block with a naturally controlled thermal environment, protected from radiation, located near ice deposits at the South Pole, represents arguably the best natural habitat option for a permanent human presence anywhere beyond Earth. Future missions are already planning to investigate specific pit entrances. Several proposed concepts involve sending small robots down into confirmed skylights to survey the interior before any human entry is considered. The tubes carry ancient lava marks on their walls. They carry the physical record of when the moon was hot and alive. And they may carry one more thing scientists are only beginning to account for: the possibility that something from Earth arrived there long ago and never left. That idea sounds extreme, but the science behind it is serious, and it starts with understanding just how violent the early solar system truly was. 4 billion years ago, Earth was being bombarded. Large asteroids and comets struck the surface constantly during a period scientists call the Late Heavy Bombardment. The impacts were enormous. Some excavated craters hundreds of miles wide. The force of each impact launched debris in all directions, including upward, away from Earth's surface and out into space. Some of that debris eventually landed on the moon. Scientists confirmed this through lunar meteorites found on Earth, which are pieces of the moon blasted off by impacts and eventually pulled in by Earth's gravity. The process works in reverse too. Pieces of Earth have landed on the moon. The physics is well understood, and computer simulations running orbital dynamics confirm that Earth-to-moon material transfer is not only possible, but inevitable, given the scale and frequency of early solar system impacts. Now here is where the question becomes genuinely uncomfortable. 4 billion years ago, life on Earth was simple, microbial, and extremely tough. Certain bacteria and archaea can survive conditions that would kill almost any other organism. They survive vacuum. They survive radiation doses that would be fatal to any animal. They can enter dormant states and remain viable for millions of years, under the right preservation conditions. If an impact ejected rock containing dormant microbes from Earth's surface, and that rock traveled to the moon and landed in a permanently shadowed crater at the poles, the cold and dark would have preserved it. No liquid water, no chemical reactions to degrade the organic material. Just frozen stasis, essentially forever. A team of scientists published a serious paper examining this exact scenario and concluded it is physically plausible. The temperatures in permanently shadowed craters are cold enough to preserve complex organic molecules and potentially dormant biological material over geological timescales. The paper is a scientific proposal, confirmed as physically possible, with the actual presence of such material remaining completely unknown. The implications sit in two directions at once. If ancient Earth material containing biological signatures landed on the moon and was preserved, the far side's cold craters might hold a record of early Earth life that Earth itself has completely erased through billions of years of geological recycling. Earth's surface replaces itself constantly through plate tectonics. Rocks from 4 billion years ago are extraordinarily rare here. On the moon, nothing recycles. The surface sits undisturbed. The moon might carry a fossil library of early Earth. The second implication is practical and urgent. Any future lunar mission that drills into permanently shadowed craters near the poles needs to carry strict contamination protocols, because any biological material found there could be ancient Earth life, modern Earth contamination from the spacecraft itself, or something else entirely. Telling those three things apart requires extreme care. No mission has yet specifically targeted a search for preserved organic material from Earth in the lunar craters. The idea remains a serious scientific proposal, awaiting the right instrument and the right landing site. But even setting aside what might be preserved there, the moon's role in Earth's habitability goes far beyond a passive neighbor. The moon actively shapes conditions on Earth in ways that most people have never been told. The connection runs deeper than tides, and understanding it requires looking at what Earth would look like if the moon had never formed at all. Remove the moon and Earth becomes a different planet. Earth's axis of rotation is currently tilted at about 23.5 degrees relative to its orbit around our star. That tilt creates the seasons. More importantly, that tilt stays remarkably stable over long timescales. Small wobbles occur over tens of thousands of years, but the axis stays within a narrow range. Life on Earth evolved around that predictable seasonal rhythm. The moon stabilizes that tilt. Gravitational interaction between the moon and Earth damps out the larger oscillations that would otherwise occur. Scientists ran the simulations. Without the moon, Earth's axial tilt would wander chaotically, potentially swinging between nearly 0 degrees and perhaps 90 degrees over millions of years on unpredictable timescales. A 90-degree tilt means the poles point directly at our star for half the year. The poles receive intense direct light, while the equator sits in near constant shadow. The resulting climate disruption would be severe. Extreme seasonal swings, massive ice sheets forming and collapsing on geologically rapid timescales. Mars, which has a much smaller moon system, has experienced dramatic axial tilt changes over its history. Scientists believe Mars's tilt has wandered from near 0 to over 60 degrees at various points. The climate record on Mars shows evidence of this instability. Ice deposits that should only exist at the poles appear at mid-latitudes, indicating periods when the tilt was radically different. Earth, with its large stabilizing moon, avoided that fate. There is a second stabilizing role the moon plays that is confirmed and directly measurable. Tidal forces from the moon slow Earth's rotation over geological time. When life was just beginning on Earth, a day lasted only about 6 hours. The moon's tidal braking has steadily lengthened the day to its current 24 hours. A faster rotating Earth has different wind patterns, different ocean circulation, different heat distribution across the surface. The rate at which Earth rotates shapes the entire climate system. The tides themselves also matter. The rise and fall of tidal zones along coastlines creates intertidal environments, regions that are wet half the time and dry the other half. Some scientists believe these zones, where ocean chemistry meets the atmosphere directly, provided conditions that helped complex organic chemistry take the step toward early life. The tidal zones act as natural chemistry laboratories, concentrating molecules, cycling wet and dry conditions, providing the right kind of instability to push reactions forward. Without a moon large enough to drive significant tides, those chemistry laboratories would be far less active. Smaller moons exist at Mars, and Mars has no tidal zones worth mentioning. The moon is not a passive object overhead. It is a gravitational anchor that has been managing Earth's stability for 4 billion years. And the reason we have such a large, well-placed moon traces back to one of the most violent events in Earth's history. An event that also explains why the far side looks the way it does, why the two worlds share so much chemistry, and why the moon's deep interior carries secrets that still resist explanation. The origin story of the moon is the origin story of everything that followed, and it is stranger than most people know. About 4.5 billion years ago, something the size of Mars hit Earth. Scientists call this object Theia, a protoplanet that formed in the early solar system and drifted into a collision course with the young Earth. The impact was catastrophic on a scale that is difficult to process. The two bodies merged partially, with material from both spraying outward in a superheated disk of vaporized rock and debris surrounding what remained of Earth. From that disk, gravity pulled the scattered material together, within perhaps 100 years by some estimates, shorter than the recorded history of most human civilizations. The moon had coalesced from the wreckage. This is confirmed science. Multiple lines of evidence point to this origin. The moon's composition is remarkably similar to Earth's outer layers. The oxygen isotope ratios in lunar rocks match Earth's so closely that the connection is unmistakable. Apollo samples confirmed this decades ago, and ongoing analysis continues to reinforce it. Theia's material blended with Earth's during the impact, and the moon formed largely from the debris of that mixture. But the details of exactly how the impact happened, what Theia was like, and what the collision geometry was, remain areas of active research. Different models predict different moon compositions and structures. Some models suggest the impact was nearly head-on. Others suggest a grazing blow. The resulting moon's internal structure should differ depending on which scenario actually happened. Here is the piece that connects back to everything discussed about the far side. If the giant impact theory is correct, the moon formed from a disk of material already chemically sorted by the violence of the collision. Heavy elements sank toward the core. Lighter silicate rock rose to the surface. The heat-producing radioactive elements we discussed earlier, the ones concentrated on the near side today, were part of that distribution from the very beginning. Some researchers believe those elements never distributed evenly across the moon after formation. They suggest the pattern was established very early, possibly within the first few 100 million years, as the moon's interior crystallized from a global magma ocean. The elements concentrated on the near side during that crystallization, driven by subtle differences in cooling rates or convection patterns in the early magma. The moon formed hot, entirely molten, and then cooled from the outside in. As it solidified, the near side, facing Earth and potentially receiving slightly different tidal heating, may have stayed molten a bit longer. That extra time allowed heat-producing elements to migrate and concentrate before the rock locked them in place. Confirmed as a process. Chemical segregation during magma ocean solidification. Confirmed as a mechanism behind the near-far asymmetry. Still debated. The models produce this pattern under certain conditions, and the observations match. But alternative explanations remain alive in the scientific community. What nobody disputes is this: the giant impact created the moon, and the moon immediately began shaping everything that followed on Earth. From the length of a day, to the existence of tides, to the stability of the seasons, the moon's presence was necessary for Earth to become what it is. And what the far side reveals about that origin story goes deeper than surface geology. Beneath the craters, the magnetic rocks, the ice and the lava tubes, the far side carries a structural record of the moon's interior that the near side has partially overwritten with volcanic activity. That structural record is now being read, and what scientists are finding in the moon's hidden gravity field is something nobody predicted would be so strange. Orbiting spacecraft do not just take pictures, they measure gravity. As a spacecraft passes over the moon's surface, variations in the gravitational field below pull it slightly faster or slower. These tiny speed changes, measurable to remarkable precision, using radio signals tracked from Earth, reveal what lies beneath the surface. Denser material pulls harder. Less dense material pulls softer. Scientists used this technique with two spacecraft that flew in tandem around the moon in 2012. They named the mission Gravity Recovery and Interior Laboratory. The two spacecraft flew one behind the other, and researchers tracked the tiny changes in the distance between them as they responded to gravitational variations below. The result was the most detailed gravity map of the moon ever produced. The near side showed what scientists expected in broad terms: dense material associated with volcanic plains, concentration of mass in large impact basins. But the far side delivered something stranger. Several large impact basins on the far side showed excess mass buried beneath them. Dense material sitting below the surface, at depths suggesting it had sunk down from above rather than welled up from below. Scientists call these concentrations of dense buried material mascons, short for mass concentrations. Mascons form when a large impact excavates the crust and the dense mantle material below rebounds upward. Over time, as the surrounding rock cools and contracts, the dense material gets locked in place beneath the basin floor. The result is a region where gravity pulls slightly harder than the surrounding terrain. On the near side, mascons under volcanic basins are well documented. The lava that later flooded those basins added additional dense material, reinforcing the effect. On the far side, the same impact basins exist, but the volcanic flooding never happened. The lava never came. So the mascons there are cleaner records of the impact dynamics alone, without the volcanic overprinting. And the far side mascons tell a different story. Some of the far side mascons are deeper than expected. The dense material sits further below the surface than the near side equivalents, suggesting the thicker far side crust locked the rebounding material before it could rise as high. The geometry implies the far side crust was already thicker at the time of those impacts than models of lunar formation predicted. Thicker earlier, locked harder, a far side that solidified faster and more completely than the near side from very early in the moon's history. This is a confirmed finding from the Gravity mission. It supports the idea of an asymmetric moon, one side cooling faster, one side staying warmer and more active for longer. And it connects directly to why the far side looks so ancient and undisturbed compared to the near side. But gravity mapping also found something the models did not predict at all. Long linear structures in the gravity signal cross the far side in patterns that do not correspond to any visible surface features. Scientists call these gravity lineaments, and their origin is debated. Some interpret them as ancient fractures in the deep crust from early cooling and contraction. Others suggest they represent ancient tectonic features from a time when the moon's interior was still dynamic. The moon had a more complicated internal life than the simple dead ball of rock it appears to be today. And if you thought the gravity map was the strangest thing hiding beneath the far side surface, the next discovery will change your expectations entirely. On the near side of the moon, there is a region unlike anything else in the solar system, roughly 3,000 miles across, covering about 16% of the lunar surface. The Procellarum creep terrain sits as a vast chemical anomaly. Its rock is unusually rich in thorium, uranium, potassium, and a collection of other elements that planetary scientists group together as KREP material, because they all tend to concentrate in the same geological environments. The name stands for potassium, rare earth elements, and phosphorus. Scientists measure its extent through gamma-ray detectors on orbiting spacecraft, which can detect the characteristic radiation signatures of these elements down through several feet of surface rock. The signal is unmistakable. Outside the Procellarum region, these elements drop to low background concentrations. Inside it, they are dramatically elevated. Confirmed through multiple orbital surveys, the chemical province is real, large, and uniquely concentrated on the near side. Here is the extraordinary part. This concentration of heat-producing elements effectively controlled the moon's entire volcanic history. As the moon cooled after its formation, the radioactive elements in the Procellarum region kept generating heat. That sustained heat source in the near-side interior maintained partial melting at depth for far longer than the surrounding regions. Whenever an impact punched through the thin near-side crust, there was molten rock waiting below to flood the resulting basin. The mare plains that cover so much of the near side formed because those craters had a heat source underneath them, ready to fill them. The far side had no equivalent heat source. Impacts struck, craters formed, but the thick crust and cold interior meant no volcanic flooding followed. The craters remained as craters. The terrain stayed ancient and rugged. One radioactive province drove the entire geological split between the two hemispheres. Scientists debate how that province formed. The most accepted model involves a process that happened during the crystallization of the lunar magma ocean. As the moon cooled from a completely molten state, minerals crystallized in a specific sequence based on their melting points. The earliest minerals formed were dense and sank. Later forming minerals were less dense and floated upward. The heat-producing elements, because of their chemistry, got excluded from early forming crystals and concentrated in the remaining melt. the last liquid fraction to solidify. This last to solidify melt, rich in incompatible elements, ended up concentrated in one region rather than distributed evenly. The reason for the concentration into a single province rather than a global layer is the part still under debate. Some models invoke a mantle plume that swept the material to one region. Others invoke asymmetric convection in the cooling magma ocean driven by the tidal heating from Earth's proximity. The Gravity mission added a clue. It found that the Procellarum region is bounded by a series of ancient rift valleys, linear structures in the crust that suggest the entire province may have formed as a separate geological unit, almost like a cap sitting on the nearside interior. The boundaries are sharper than a gradual chemical gradient would produce. A cap of radioactive rock on one side of the moon, a blank, cold, thick crust on the other. And in between, a mystery about why those two worlds, which formed from the same debris at the same time, ended up so completely different. An answer to that mystery might require us to consider something even more extreme, something the solar system seems to do more often than its peaceful present would suggest. In 2011, two planetary scientists named Martin Jutzi and Eric Asfalg published a proposal that changed how researchers thought about the moon's history. They suggested the moon formed with a companion. When the giant impact created the debris disk around Earth, the disk did not necessarily produce just one large object. Computer simulations of the impact and subsequent disk dynamics show that in some scenarios, two large objects can emerge: a primary moon and a smaller companion body, perhaps a quarter to a third the size of the moon we have today. Both would initially orbit Earth at similar distances, locked in a gravitational arrangement similar to what mathematicians call a Lagrange configuration, where smaller bodies can orbit stably near larger ones. This arrangement is not permanent. Over millions of years, tidal interactions would have caused the two moons to drift and eventually, slowly, to approach each other. Jutzi and Asfalg modeled the collision between these two moons and found a specific scenario that produces the lunar dichotomy we observe. A low-speed collision, far slower than the initial giant impact, would not shatter the larger moon. Instead, the smaller body would effectively splat onto the far side, depositing a thick layer of crustal material asymmetrically. This is still a hypothesis, confirmed as consistent with observational data, classified scientifically as a serious theoretical proposal, not yet verified by direct physical evidence from a sample. But the evidence that could support it keeps accumulating. The thicker far side crust fits. A second moon piling onto the far side would leave exactly the crust thickness profile observed. The absence of volcanic maria on the far side fits. Added crustal thickness means a harder barrier for volcanic material to penetrate. The unusual chemistry of the far side highlands fits. Material from a second moon of different composition would leave a distinct chemical fingerprint in the crust. There is also a subtle structural argument from the topography. The far side crust has a slightly different internal structure than the near side crust, even at similar depths. Some of that structural difference is consistent with material being added from outside, rather than simply cooling in place. One piece of evidence that researchers point to carefully is the nature of the far side highland rocks themselves. The aluminum-rich rock that dominates the far side highlands could be consistent with material that originated in a separate, differentiated body. If the companion moon had its own magma ocean and its own crystallization sequence, it would have developed a crust with slightly different chemistry than the primary moon's crust. The next step in testing this hypothesis requires direct sampling of far side highland material from diverse locations, not just the basin floors where Chang'e 4 landed. That sampling has never been done. Future missions targeting the far side highlands are being proposed specifically to collect this kind of material. If the second moon hypothesis is confirmed, it fundamentally changes the story of the moon. Every time we look at the far side's battered surface, we would be looking at a symmetry of its sibling, absorbed billions of years ago, without a trace except for the thickness of a crust and the silence of volcanoes that never came. And hidden inside that crust are signals that reach back even further than the moon's birth, signals that could show us the universe before any star ever turned on. The far side of the moon has a quality that no other location accessible to us shares. Earth is loud. human civilization generates massive amounts of radio frequency radiation. Television broadcasts, mobile networks, radar systems, satellites, power lines, all of it produces electromagnetic noise that floods the radio spectrum and drowns out faint signals from the cosmos. Even in the most remote locations on Earth, the planet's own ionosphere reflects certain low-frequency radio waves back inward, creating an unavoidable layer of interference. Radio astronomers on Earth work constantly to filter out this noise. Some wavelengths cannot be observed from Earth's surface at all, because the ionosphere blocks them entirely. The far side of the Moon solves this problem completely. With the entire Moon sitting between the far side and Earth, every source of human-made radio interference is blocked by 2,000 miles of solid rock. The far side is the most radio-quiet environment within practical reach of a spacecraft. And in that silence, signals become audible that are impossible to detect anywhere else. The signals scientists most want to hear in this silence are called the cosmic dark ages. After the Big Bang, the universe went through a period of hundreds of millions of years before the first stars formed. During this time, the universe was filled with neutral hydrogen gas, spread through space in vast clouds. Hydrogen emits a specific radio signal at a wavelength of about 8 inches, called the 21 centimeter line. As the universe expanded during the Dark Ages, that wavelength got stretched by cosmological expansion into much longer radio waves, now in the range of several meters to tens of meters. These extremely long radio waves are precisely the ones blocked by Earth's ionosphere. They cannot be observed from Earth's surface. Observing them requires either a space-based antenna or a location shielded from Earth's radio noise. The far side of the Moon is ideal for both reasons. It is shielded from Earth's noise, and it can carry antennas on a stable platform with no atmosphere to absorb the signals. Mapping the distribution of hydrogen gas during the cosmic dark ages would give scientists a direct picture of the universe before the first stars formed. It would test theories about how matter clumped together under gravity in the early universe. It could reveal signatures of the first structures that eventually became galaxies. Confirmed scientific objective. No instrument has yet observed the dark ages from the lunar far side, though several missions have proposed carrying the necessary equipment. A Chinese spacecraft called Chang'e 7, planned for later this decade, includes proposals for radio astronomy experiments. A separate multinational concept proposes deploying a large antenna array on the far side surface. If it works, astronomers from the far side of the Moon would effectively be looking backward in time, further than any telescope has managed from Earth, or even from orbit. The Moon would become humanity's deepest eye into the past. But before that vision becomes possible, a problem needed to be solved that is completely unique to the far side. How do you talk to a spacecraft on a surface that can never see Earth? A spacecraft on the far side of the Moon faces a fundamental communication problem. From the far side surface, Earth sits permanently below the horizon. Always. There is no sunrise for Earth over there, no brief window of line-of-sight contact. The Moon sits between the spacecraft and home, 2,000 miles of solid rock blocking every signal in every direction. Every previous lunar mission landed on the near side or in orbital paths that maintained contact with Earth directly. The far side was unreachable for this exact reason. Not just difficult, physically impossible to communicate with using direct contact. China solved this problem before Chang'e 4 ever launched. In May of 2018, China placed a relay satellite into a special orbit called a halo orbit around the second Lagrange point behind the Moon. This is a mathematically stable region in space, roughly 37,000 miles beyond the Moon's far side, where a satellite can orbit in a way that keeps it visible to both the far side surface and to Earth simultaneously, using the natural gravitational balance of the Earth-Moon-Sun system. The satellite is called Queqiao, which translates roughly to Magpie Bridge, a reference to a Chinese folk tale about a bridge built across the sky to allow separated lovers to reunite. The name was deliberately chosen. The satellite's position is confirmed stable for years. It carries antennas pointing toward the lunar far side and toward Earth, acting as a relay station in space. Every command sent from Earth to Chang'e 4 traveled up to Queqiao first, then down to the Moon's far side. Every piece of science data, and every image traveled the reverse path. Without Queqiao, the far side was forever silent from our perspective. With it, communication became possible. The engineering behind the halo orbit is elegant in a way that resembles a celestial magic trick. The satellite does not orbit the moon directly. It orbits an empty point in space, a mathematical location defined by the gravitational balance between Earth and Moon. Keeping a spacecraft at that point requires periodic small thruster firings to maintain position, but the orbit is stable enough that Queqiao has operated continuously since its deployment. The success of Queqiao opened the door to a new era of far-side exploration. Any future lander, rover, or human mission to the far side will depend on relay satellites of this kind. Scientists and engineers are already designing next-generation relay systems with higher bandwidth and longer operational lifetimes to support more ambitious missions. There is also a scientific application for the relay satellite itself. Queqiao carried a low-frequency radio antenna on a long deployable boom. From its position behind the moon, it conducted early observations attempting to detect long-wavelength radio signals in the radio-quiet shadow of the far side. The results were preliminary, but they confirmed the far side's radio environment is as clean as scientists predicted. The silence behind the moon is real, and something waits to be heard inside it. But the story of how humanity reached the far side at all, the decisions made, the missions launched, the technology built, points toward a deeper race that is only beginning. Multiple nations are now targeting the far side of the moon specifically because of what the science says is there. And among the strangest chapters of that science story is one that requires going back to the moon's deep interior, where something about the core itself may explain a mystery that has puzzled scientists since the first Apollo samples came home. The moon has a core. Scientists confirmed this through seismic data collected by instruments that Apollo astronauts placed on the surface decades ago. Moonquakes travel through the interior and arrive at surface sensors with timing patterns that reveal the internal structure. The moon has a small iron-rich inner core, surrounded by a fluid outer core, surrounded by a partially molten layer called the mantle transition zone, surrounded by the solid mantle and crust. The core is small relative to the moon's overall size. Earth's core makes up about 30% of its mass. The moon's core makes up roughly 1 to 2%, small but confirmed real. Here is the problem. The moon once had a global magnetic field. We know this because lunar rocks carry ancient magnetic signatures, imprinted when they cooled while a field was present. The field appears to have been strongest around 3 to 4 billion years ago, and then weakened and eventually collapsed. Scientists believe the field was generated by convection in the fluid outer core, same basic mechanism as Earth's field. But the moon's core is tiny. Generating a global field through core convection in such a small core is difficult to explain with straightforward models. And the timing of the field's collapse, combined with the magnetic anomalies concentrated on the far side, suggests the process was not uniform. Recent analysis of lunar samples and seismic data suggests the lunar core may be asymmetric. One side of the core may have solidified differently or at a different rate than the other. Crystallization in the inner core produces a release of light elements and heat that drives convection in the outer core. If that crystallization happened preferentially on one side, the convective patterns that generated the magnetic field would have been asymmetric too, generating stronger fields in some directions, weaker in others, and explaining the uneven distribution of magmatized rock across the lunar surface. The far-side magnetic anomalies that appeared in Chapter 4 would fit this picture. A core generating an asymmetric field would leave stronger magnetic imprints in certain hemispheres. The far side, receiving stronger field lines during the period when its rocks were last cooling, would carry stronger frozen magnetic signatures. This hypothesis is supported by computer models of core dynamics and by the distribution of known magnetic anomalies. Scientists consider it plausible and consistent with available evidence. Their direct measurement of the deep core structure requires seismometers more sensitive than anything placed on the moon so far. Planned missions aim to change that. Proposals for a lunar geophysical network, multiple seismometers distributed across both the near and far sides, have been part of scientific mission planning documents for years. Such a network would resolve the core structure question definitively. If the asymmetric core hypothesis is confirmed, it would explain the magnetic anomalies, reinforce the idea of a moon that cooled unevenly, and provide a detailed case study of how planetary cores evolve after their magnetic fields die. Understanding that process in detail has direct applications to understanding what happened to Mars, why Venus has no field, and what the long-term fate of Earth's own core looks like. A dead moon's frozen interior carries a lesson about every living planet in the solar system, and what that interior tells us about the moon's future, and Earth's future alongside it, leads to a chapter that connects everything we have explored so far into a single, continuously unfolding story. The moon is still moving, still changing, still affecting us right now, and the rate at which it is leaving may tell us how much time we have before something important shifts forever. Every year, the moon moves about 1.5 inches farther from Earth. That sounds trivial, but over geological time, it compounds into something significant. 4 billion years ago, the moon was dramatically closer, roughly 3 times nearer than today. Earth's rotation was faster. Tides were vastly more powerful, and the gravitational interaction between the two bodies was more intense. The mechanism behind this drift is confirmed physics. The moon's gravity raises tidal bulges on Earth, both in the oceans and in the solid rock of the crust. Earth rotates faster than the moon orbits, which means those bulges are always slightly ahead of the moon in the direction of rotation. The moon's gravity pulls back on those bulges, slowing Earth's rotation slightly. By Newton's third law, the bulges pull forward on the moon, adding a tiny amount of energy to its orbit. Energy added to an orbit raises it, so the moon gradually spirals outward. Earth's rotation slows, the moon's orbit grows. Angular momentum conserves. A confirmed, well-measured process. Scientists measured the recession rate using lasers bounced off retroreflectors left on the lunar surface by Apollo astronauts. The distance to the moon can be measured to within fractions of an inch using this technique. The drift rate of about 1.5 inches per year is one of the most precisely measured facts in planetary science. But this drift has a consequence that most people overlook. The moon's apparent size in our sky is a coincidence of the current moment. Right now, the moon sits at a distance that makes it appear almost exactly the same size as our star from Earth's perspective. This is why total solar eclipses happen. When the moon passes directly in front of our star, it covers the disk almost perfectly, allowing scientists to study the outer atmosphere of our star in ways impossible otherwise. Observations of this outer atmosphere during eclipses have revealed structures and dynamics that shaped entire branches of solar physics. That perfect alignment is temporary. The moon is moving away. In about 600 million years, the moon will be too far and too small to fully cover our star's disk. Total solar eclipses will end. We happen to live at the one window in Earth's history when the geometry works out precisely. The same drift also means that in the deep past, when the moon was closer, its tidal influence on Earth was far more powerful. The tides that may have helped kickstart life in intertidal zones were stronger. The day was shorter. The climate was shaped differently. The moon we study today is a snapshot of an ongoing process. The relationship between Earth and moon has been dynamic from the beginning and continues to be dynamic right now. And what that relationship will look like billions of years from now, when the moon has drifted further, when Earth's rotation has slowed to match the moon's orbital period, when the two bodies reach a final tidal lock, where Earth shows only one face to the moon as the moon now shows only one face to Earth, is a planetary fate already experienced by other worlds. The moon is teaching us about time, about the long arc of gravitational physics that governs every rocky world in the solar system. And somewhere in the far side's ancient crust, in its frozen craters and its magnetic rocks and its silent lava tubes, the record of how all of this began is still waiting to be read in full. What comes next will reach even deeper into that record, into questions that no spacecraft has yet answered, and that future missions will travel to the far side, specifically to resolve. The rover rolled slowly across the floor of the von Karman crater, and its instruments were finding things that did not belong on a surface. Chang'e 4 carried a spectrometer that analyzes the chemical composition of materials by measuring how they reflect different wavelengths of light. Every mineral has a signature, a specific pattern of absorbed and reflected light that acts like a fingerprint. Point the instrument at the ground, and it tells you what the rock is made of. On the crater floor, the spectrometer found olivine and low calcium pyroxene, together in concentrations pointing to a deep origin. These two minerals form at high pressure and high temperature, deep inside a planetary body. They are the building blocks of the mantle layer beneath the crust. Finding them sitting exposed on the surface means something brought them up from depth. The leading explanation is the South Pole Aitken Basin impact itself, an impact that enormous, striking with enough force to punch through the crust and excavate the upper mantle, would have sprayed mantle material across the surrounding terrain. The Von Karman crater sits inside this basin, so the floor should be littered with debris from that ancient excavation. Confirmed as the most likely source by the science team, the minerals match what mantle origin predicts, but the proportions surprised scientists. The standard model of how the moon's interior crystallized from its early magma ocean predicts a specific ratio of olivine to pyroxene in the upper mantle. The Chang'e 4 measurements found less olivine than expected. Pyroxene dominated. Either the moon's mantle has a different composition than the models assumed, or the impact mixed mantle material with crustal material in ways that diluted the olivine signature. Or the moon's magma ocean cooled in a sequence that produced a different mineral distribution than the current model describes. Each of those possibilities carries major implications. A differently composed mantle means the moon's formation conditions were different from what simulations currently describe. A different cooling sequence changes the timeline of lunar evolution. A complex mixing by the impact requires revising how scientists interpret minerals found anywhere inside large impact basins across the solar system. Here is what makes this discovery especially important. The Moon is the most accessible planetary body with an exposed mantle. Mars has a thick crust with no confirmed mantle exposures accessible for a rover. Mercury's surface geology is complex and less studied. Venus is entirely inaccessible at the surface. The Moon, sitting a few days away by spacecraft, offers a sample of deep planetary interior that we can actually drive a rover across. Every measurement from the Von Karman floor is a data point about how rocky planets form, differentiate, and evolve from the inside out. Scientists want more measurements. One crater floor is a single window into the mantle. Sampling different locations around the South Pole Aitken Basin would reveal whether the mineral proportions vary across the basin or hold consistent, which would distinguish between the mixing hypothesis and the compositional hypothesis. Future missions are being planned with exactly this goal. The surface of the far side is an open laboratory, and the experiments have barely begun. And what those future experiments will be looking for goes far beyond minerals. Something in the deep subsurface of the far side has been actively resisting every attempt to explain it cleanly. A structural feature so large it shows up in gravity data, but has never been physically sampled. A buried mass that alters spacecraft orbits and sits at a depth that no drill has ever reached. What is buried beneath the South Pole Aitken Basin floor may be the most significant unresolved question in lunar science. Gravity does not lie. When the two spacecraft of the Lunar Gravity Mapping Mission flew over the South Pole Aitken Basin, they detected an anomaly in the gravitational signal, so large that scientists initially double-checked their instruments. Beneath the basin floor, something with extraordinary mass was concentrated at depth, pulling on the spacecraft with measurably more force than the surrounding terrain. A team published their analysis and described the anomaly as having a mass roughly equivalent to a large metallic object buried in the mantle beneath the basin. Their best estimate placed the excess mass at several hundred miles wide, sitting at a depth of roughly 100 miles below the surface. The leading hypothesis is that this buried mass is a dense metallic core fragment from the asteroid or comet that created the South Pole Aitken Basin in the first place. When a large impactor strikes a rocky body, the collision does not simply vaporize everything neatly. The dense metallic core of a differentiated impactor, meaning one that had its own iron-rich center, can survive partially and sink into the target body's interior during the chaos of the impact. The heat and pressure drive it downward. The surrounding mantle, temporarily liquefied by the impact energy, allows it to descend before the rock solidifies again. The metallic fragment then freezes in place deep in the mantle, preserved for billions of years. If this is what happened at the South Pole Aitken Basin, the metallic mass sitting beneath the far side right now is a relic of the actual object that carved the solar system's largest confirmed impact crater. A piece of the impactor, frozen inside the moon, 4 billion years old. Scientists consider this the most consistent explanation for the gravity data. Confirmed as a credible hypothesis consistent with the mass and depth indicated by the measurements, confirmed as unverified because nothing has yet drilled anywhere near that depth. 100 miles is far beyond any current drilling technology applicable to a planetary surface. Earth's deepest borehole reaches barely 8 miles. Reaching the buried anomaly directly is a generational engineering challenge, far beyond anything planned for the coming decades. But scientists do not need to touch it to study it. Seismic waves traveling through the moon's interior would pass through that dense object and arrive at surface seismometers with a timing signature different from waves passing through normal mantle rock. A network of seismometers distributed across the far side would detect those differences and allow scientists to map the buried mass precisely without drilling. That seismic network does not yet exist. Apollo placed seismometers on the near side. The far side has had none. Plans for a geophysical network mission have circulated in the scientific community for years, appearing in lunar science priority documents repeatedly as a high-value target. Here is why this buried object matters beyond satisfying curiosity about a single impact. If the impactor's core survived and sank, it means the early moon's interior was hot and mobile enough to allow dense material to descend through it. That tells scientists about the moon's thermal state immediately after its largest impact. It constrains how fluid the early lunar mantle was. It provides a data point for models of how planetary interiors respond to catastrophic impacts across the solar system. Every rocky world in the solar system bears impact scars. Every one of them received large impactors during the heavy bombardment. How those impactors' cores behaved after striking their targets, whether they survived, sank, mixed, or vaporized, is a question with implications across planetary science. The far side of the moon holds a frozen answer, and getting to that answer will require missions more ambitious than anything yet landed there. What those missions find will not stay isolated as lunar science. It will feed directly into one of the biggest questions currently driving space exploration. How do you build a permanent human outpost beyond Earth? And the far side, for all its strange science, may be the most practical location for humanity's first permanent off-world home. Building a permanent base on the moon requires solving several problems simultaneously. Radiation is the first. The lunar surface has no atmosphere, and only those scattered patches of ancient magnetism to partially deflect incoming particles. Cosmic rays and solar energetic particles hit the surface constantly. During a major solar storm, the radiation dose on the lunar surface could reach levels dangerous to human health within hours. Any permanent habitat needs shielding that either comes from the construction materials brought from Earth, which is expensive and limited, or from the moon itself. The second problem is thermal cycling. Surface temperatures on the moon swing from about 250 degrees Fahrenheit during the 2-week lunar day down to minus 290 degrees at night. Equipment and habitats must withstand this range repeatedly over years of operation. Building structures that handle those swings adds engineering complexity and cost. The third problem is micrometeorites. Small particles traveling at miles per second strike the lunar surface continuously. On Earth, the atmosphere burns them up. On the moon, they reach the surface directly. Over time, they degrade exposed materials and pose a risk to anything with a pressurized interior. The lava tubes discussed earlier solve all three problems at once. Confirmed from theoretical analysis and orbital data, tubes of sufficient depth and thickness provide complete radiation shielding against cosmic rays and solar particles. The rock roof absorbs the incoming particles before they reach the interior. A tube with even 30 feet of solid rock overhead provides roughly the same radiation protection as Earth's surface. The temperature inside a deep lava tube stays nearly constant, around minus 30 degrees Fahrenheit, across all times of the lunar day and night. Cold, but manageable and stable. Stable temperature means far simpler thermal engineering for habitats inside. And micrometeorites cannot penetrate solid rock. The tube interior is completely protected. Beyond the physical protection, the far side location of several candidate tube structures sits near the South Pole, within range of the confirmed ice deposits. A permanent base inside a lava tube near the pole would have access to water ice for drinking, agriculture, and fuel production. The proximity to the South Pole Aitken Basin means the scientific targets discussed throughout this video, the exposed mantle minerals, the buried gravity anomaly, the magnetic rocks, the ancient crust samples, are all within rover range. From a purely resource and logistics standpoint, the far side near the South Pole is arguably the most strategically valuable location on the Moon. The communication challenge remains. Any permanent base on the far side requires a dedicated relay satellite network, at minimum, one Queqiao-type satellite in the halo orbit position, and ideally, multiple satellites for redundancy and higher bandwidth. China's experience with Queqiao proved the concept works. Next-generation relay systems are already being designed by multiple agencies. There is a scientific bonus to basing humans on the far side that goes beyond geology. Human-tended radio observatories on the far side, taking advantage of the electromagnetic silence, would have access to wavelengths and sensitivities impossible anywhere else. A scientist operating instruments from inside a lava tube, shielded from radiation, in the most radio-quiet environment in the inner solar system, could conduct observations that transform multiple fields of astronomy simultaneously. The far side was once the unreachable unknown. It may become the most scientifically productive address in the solar system. But before permanent habitation, before radio observatories and geological drills, the missions currently in planning need to answer a question that has been quietly generating controversy in the lunar science community. A question about what happened to the water on the early Moon, and whether far more of it survived than anybody thought. The Moon formed violently hot. The giant impact that created the Moon vaporized rock. The early Moon was a magma ocean, a completely molten surface exposed to space, radiating heat away as it cooled. Under those conditions, water should have boiled off immediately. Volatile compounds like water cannot survive in a magma ocean. The scientific consensus for decades was that the Moon formed bone dry. Then the samples came back. Instruments sensitive enough to detect trace amounts of water in rock found hydroxyl groups, the chemical fragment of water locked inside volcanic glass beads, collected during Apollo missions. The amounts were tiny, measured in parts per million, but they were real, and they were distributed throughout the samples from multiple sites, suggesting the source was internal rather than contamination. Scientists confirmed the Moon's interior contains water, not a surface layer, but water dissolved into the mantle rock itself during formation, preserved through billions of years of geological history. The amount is still debated. Some estimates suggest the lunar mantle could contain water concentrations comparable to Earth's mantle in certain regions. If that is true, the total water stored inside the Moon is far larger than anyone originally calculated. How did it survive the violent formation? One possibility is that some of the water was incorporated into the deep mantle minerals during the crystallization of the magma ocean, before the surface fully solidified, trapped inside mineral structures that held onto it even at high temperatures. Another possibility involves material that arrived on the Moon after the main formation event, but before the surface cooled completely. Comets and water-bearing asteroids, contributing to a late inventory. For the far side, this internal water story carries a specific implication. The mantle material exposed on the floor of the von Karman crater, the olivine and pyroxene detected by Chang'e 4, comes from those deep internal layers. If the mantle contains dissolved water, then those exposed minerals should too. Future missions equipped to measure water content in exposed mantle rock on the far side floor would directly test how much water survived inside the Moon from its earliest history. The amount of primordial water in the lunar interior has direct bearing on models of how rocky planets in general acquire and retain water. Earth is wet, Mars is dry today but may have been wetter. Venus lost its water entirely. Understanding the process that determines how much water a rocky planet keeps requires data points across multiple worlds. The Moon, accessible and geologically ancient, provides a critical reference, and the water story on the far side does not end with the mantle. Permanently shadowed craters have confirmed ice. The mantle may have internal water. The impactors that struck the early Moon brought water from the outer solar system. Water arrived and stayed in multiple forms, through multiple mechanisms, across billions of years. The Moon is wetter than the textbooks written 20 years ago described. And that wetness has a direct connection to whether life could have existed there, even briefly, and whether the resources needed for human expansion into the solar system are already sitting in place waiting. What else is sitting in place, undetected, beneath the far side's ancient surface, requires one more layer of geological history that even dedicated researchers sometimes overlook. The volcanic past of the far side left behind, features that are only now being mapped in full detail. The far side never experienced the dramatic volcanic flooding that covered the near side in dark plains. That much is confirmed. But saying the far side had no volcanic activity at all is an overstatement. Scattered across the far side are features that scientists call irregular mare patches, small isolated deposits of volcanic material, dramatically younger than the ancient highland crust surrounding them. Some of these deposits are estimated to be only 100 million years old. On a moon whose main volcanic era ended roughly 3 billion years ago, that is extraordinarily recent. 100 million years ago, on Earth, dinosaurs were alive. These small volcanic features are too limited in extent to reshape the far side landscape. They cover areas sometimes only a few miles across, tiny compared to the massive lava plains on the near side. But their existence proves that something in the lunar interior was still capable of generating and delivering magma to the surface long after the main volcanic period ended. Scientists debate the source of that late-stage activity. One explanation involves localized concentrations of radioactive heat-producing elements in specific parts of the far side mantle, similar in principle to what drove near-side volcanism, but smaller in scale and scattered in distribution. A pocket of creep-like material in the far side mantle would generate just enough heat to drive occasional small eruptions over an extended period. A second explanation involves impact triggering. Large impacts in the geologically recent past could have generated enough localized heat and pressure relief to allow small amounts of already warm mantle material to reach the surface through fractures in the crust. Several of the small volcanic deposits on the far side sit near or inside moderate-sized craters. A third possibility, more speculative, but supported by some thermal models, is that the Moon's mantle is not as completely solidified as commonly assumed. If small pockets of partially molten rock persist in specific deep locations, sustained by residual radioactive heat or tidal flexing, they could occasionally produce surface eruptions, given the right conditions. Confirmed. These young volcanic deposits exist. Their exact age and mechanism remain areas of active research. For the far side specifically, the importance of these features goes beyond geological curiosity. If small volcanic systems persisted on the far side into the geologically recent past, the far side interior is warmer and more active than the simple cold dead model describes. That warmth could affect the stability of the ice in permanently shadowed craters over time. A warmer local interior raises the background heat flow, which influences the temperature profile of the polar craters from below. More practically, volcanically young terrain on the far side represents recently refreshed surface material. Rock from younger volcanic activity has not been gardened by billions of years of micrometeorite impacts, which churn the upper few feet of lunar soil into a fine powder called regolith. Fresh volcanic rock sitting in a low regolith patch on the far side could provide geochemical information about the Moon's recent interior state that ancient highland rock cannot offer. No mission has yet specifically targeted one of these young volcanic deposits on the far side. They appear in orbital data as distinct spectral anomalies, identifiable from orbit but unvisited at ground level. A rover mission sent to one of these patches would be sampling material from a geologically recent event on a world most people think has been inactive for billions of years. The far side keeps offering layers of activity, magnetism, water, heat, and volcanism that the simple image of a dead-cratered world does not capture. And some of the most surprising layers have nothing to do with geology at all. They have to do with time, with signals from so far in the past that the physics connecting them to the present requires the entire history of the universe to bridge the gap. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before that moment, space was filled with a plasma so hot and dense that light could not travel through it. The moment atoms formed, the universe became transparent. Light could finally move freely. That light is still traveling today, stretched by 13.8 billion years of expansion into microwave radiation that fills the entire sky. Scientists call it the cosmic microwave background, and telescopes have mapped it in extraordinary detail. But between that first light and the ignition of the first stars, there was a gap, hundreds of millions of years, where the universe was dark, filled with neutral hydrogen gas, slowly clumping under gravity into the first structures. Scientists call this the cosmic dark ages. During those dark ages, hydrogen atoms were constantly emitting and absorbing a specific radio signal. The physics of the hydrogen atom allows electrons to flip between two energy states in the nucleus, releasing or absorbing a photon with a wavelength of about 8 inches each time. This is called the 21 centimeter line. The Dark Ages hydrogen signal has been stretched by expansion. What was emitted at 21 centimeters during the Dark Ages arrives at Earth today at wavelengths between about 3 and 30 feet, sitting in the long-wave radio part of the spectrum. Those exact wavelengths are blocked by Earth's ionosphere completely. A radio telescope on Earth cannot detect them regardless of how remote its location. The physics of the ionosphere makes observation from Earth's surface impossible. From orbit, spacecraft have attempted partial observations, but Earth itself emits enormous amounts of radio frequency interference that contaminates the signality needed. The far side of the Moon removes both problems simultaneously. Confirmed by radio frequency surveys, the far side's electromagnetic environment is the cleanest in the accessible solar system. The Moon's bulk blocks every human-generated signal from Earth. The far side has no ionosphere of its own. The long-wave radio signals from the cosmic dark ages can reach a receiver on the far side surface without obstruction. A radio telescope array on the far side surface, even a relatively modest one by Earth standards, could detect the 21 centimeter signal from the dark ages and map the distribution of hydrogen across the early universe. That map would reveal how matter was distributed in the universe before the first stars turned on, where the first galaxy seeds were forming, and how the large-scale structure of the cosmos emerged from the nearly uniform plasma of the early universe. Every major cosmological model makes predictions about what that hydrogen distribution should look like. Those predictions differ in specific, testable ways. Detecting the Dark Ages signal would discriminate between models in ways that no current or planned Earth-based or orbital telescope can achieve. Scientists describe a Dark Ages radio telescope on the far side as potentially the highest return astronomical investment possible, given current technology, a confirmed scientific priority listed in multiple international astronomy roadmaps. No such telescope yet exists on the far side. The engineering challenges are real. Deploying a large antenna array on the far side surface, powering it, transmitting data through a relay satellite, requires significant infrastructure. But the concept is feasible with technology available today or in development for near-term missions. Humanity has spent centuries building bigger and better telescopes. The next transformative leap in observational cosmology may require building the first telescope in the most unusual location we have ever reached. And the observations made from that location will not only look backward in time, they will also answer a question about our own existence that sits at the intersection of astronomy, chemistry, and the deepest mystery in planetary science. Why does Earth have life? The question seems obvious at first. Earth has liquid water, a stable climate, an atmosphere, a magnetic field, and the right distance from its star. These conditions are understood. What is less understood is whether those conditions emerged inevitably from Earth's physical setup, or whether the Moon's specific role was a necessary ingredient. The Moon stabilizes Earth's axial tilt, Confirmed. The moon drives tides. Confirmed. The moon's tidal braking set the length of Earth's day at a value that some researchers argue provides the right rate of day-night cycling for photosynthesis and climate stability, though this connection remains an active area of study rather than confirmed necessity. But there is a deeper version of this question. Life on Earth requires organic chemistry, complex carbon-based molecules that can store information, catalyze reactions, and eventually replicate. The building blocks of that chemistry are common across the solar system. Comets carry amino acids. Asteroids carry sugars and nucleobases. The raw ingredients exist in space widely. The question is how those ingredients assembled into something that could replicate and evolve. The leading environments proposed for that assembly include deep-sea hydrothermal vents, warm shallow ponds with wet-dry cycling, and tidal zones where ocean water repeatedly concentrates and dilutes over surfaces. Tidal zones depend on tides. Tides depend on the moon. 4 billion years ago, the moon was much closer. Tides were vastly more powerful. The tidal zone on early Earth was not a narrow strip of coastline. Researchers estimate the tidal range covered hundreds of vertical feet in some coastal areas, creating vast landscapes that flooded and drained on a 6-hour cycle driven by both tidal forces and rapid Earth rotation. In those rapidly cycling, chemically concentrated zones, the conditions for the kind of complex chemistry that produces self-replicating molecules may have been far more favorable than any other environment on early Earth. Remove the moon, or give Earth a smaller moon that produces weaker tides, and the tidal zone shrinks dramatically. The chemistry that may have sparked life either slows down, or finds a less favorable environment, or may not happen at all. This is a hypothesis, not a confirmed causal chain. Scientists cannot run a controlled experiment with a moonless Earth. But the physical connections are real. The tidal chemistry models are supported by laboratory work, and the timing aligns. The moon was closest and most influential during the exact period when life first appeared on Earth. Here is the broader implication. If large moons are necessary for life on rocky planets, then life may be rarer than optimistic estimates suggest. Giant impact events that produce large moons are not a guaranteed outcome for every rocky planet. They require a specific collision geometry, at the right time, with the right-sized impactor. Most rocky planets may go through their formation without one. The far side of the moon carries the evidence of that ancient giant impact in its very structure. The thick crust, the exposed mantle minerals, the ancient magnetic signatures, all of them trace back to the same original event. Every mystery we have explored throughout this video connects back to one collision 4.5 billion years ago. That collision may have been the reason you exist. And scientists are now designing the next generation of missions specifically to probe the physical record of that event in places no spacecraft has yet landed, asking questions that the near-side samples from Apollo could never answer. The far side of the moon is no longer a destination for the distant future. Multiple space agencies have active programs targeting it within this decade. China's Chang'e 6 mission, launched in 2024, completed the first ever sample return from the far side. It landed inside the South Pole Aitken Basin, collected material from the surface, and returned it to Earth. Scientists are currently analyzing those samples. The initial findings indicate material with a composition distinct from near-side Apollo samples, consistent with the deep basin floor origin predicted by models. Analysis continues with results expected across multiple scientific papers over the coming years. This achievement is significant in a way that goes beyond the scientific content of the samples themselves. It proved that robotic sample return from the far side is achievable. The engineering challenges of landing, drilling, collecting, launching from the surface, and returning through the relay satellite system were all solved simultaneously. China also has Chang'e 7, planned for the lunar South Pole, carrying instruments including ground-penetrating radar, heat flow probes, and radio astronomy payloads. The mission targets the permanently shadowed craters and their ice deposits with more specialized instruments than any previous lander. India's Chandrayaan missions have focused on the South Pole region from orbit, and with a lander mission that targeted the near South Pole. Future Indian lunar missions include surface science components aimed at characterizing the polar environment. Multiple private companies are developing commercial landers targeting the South Pole under contracts with space agencies. Several carry science payloads, including seismometers, which would begin building the distributed sensor network needed to map the moon's internal structure. The United States and international partners are planning crewed lunar landings at the South Pole under the Artemis program. The science objectives for those crewed missions include sampling both the permanently shadowed ice deposits and the ancient highland material surrounding the South Pole Aitken Basin. Here is what makes the coming decade so significant. For the first time in history, the far side will be visited by multiple missions from multiple nations carrying complementary instruments. Seismometers from one mission will measure moonquakes, while heat flow probes from another measure thermal gradients. Sample return from one landing site will be compared against remote sensing data from an orbiter covering the entire basin. Radio astronomy receivers will listen while geochemists analyze rocks. The combination of instruments, rather than any single discovery, will answer the questions that have resisted decades of orbital observation. The asymmetric crust, the buried gravity anomaly, the mantle water content, the ancient magnetic fields, the origin of the late volcanic deposits. All of these require the kind of coordinated, multi-instrument surface science that only a sustained campaign of missions can deliver. The far side is transitioning from a mystery observed at a distance into a laboratory being actively investigated on the ground. And the scientists designing these missions are working with a sense of urgency, because several of the questions the far side can answer connect to decisions humanity needs to make about its own future in space within the next 50 years. Where the first permanent base will go, how to protect humans from radiation, where the water and fuel will come from, what the moon's interior structure means for understanding every other rocky world we might want to reach. The far side secrets are not just historical curiosities, they are operational intelligence for the next era of exploration. The top layer of the moon's surface is not soil, it is a record. Over billions of years, micrometeorite impacts have pulverized the surface rock into a fine powder called regolith. The particles range from microscopic glass beads to fragments the size of gravel. The regolith blankets the entire lunar surface, reaching depths of several feet in ancient highland terrain and dozens of feet in some older regions. On the near side, this regolith has been studied through Apollo samples for decades. Scientists know its composition, its mechanical properties, the sizes of its particles, and the history of solar radiation embedded in its chemistry. But the near-side regolith reflects a near-side geological history: volcanic plains, radioactive province influence, younger surface ages in the basalt-covered Maria. The far-side regolith is different because the far-side crust is older and the surface has never been resurfaced by lava flows. The regolith there is generated from ancient highland rock. It carries a different mineral baseline, and because the far side receives more direct cosmic radiation exposure without any nearby geologically young material to mix in, the oldest layers of far side regolith may preserve a continuous record of solar wind and cosmic ray bombardment stretching back over 4 billion years. The solar wind carries particles ejected from our star. Those particles embed themselves in the top layers of exposed surface minerals. Over time, the regolith accumulates a chemical record of how energetic and compositionally variable the solar wind has been across geological history. Studying that record tells scientists how the behavior of our star has changed over billions of years, a question with direct implications for understanding solar activity cycles, solar weather forecasting, and the conditions early Earth experienced. Cosmic rays from beyond the solar system also leave signatures in regolith grains. The intensity of cosmic radiation at Earth's location in the galaxy has varied as the solar system traveled through different regions of the Milky Way over its long orbit around the galactic center. Far-side regolith, undisturbed by volcanic resurfacing, could carry a record of those galactic scale changes. Confirmed science: regolith carries these embedded records. Confirmed: far-side regolith is older and less disturbed than near-side equivalents. What specific information those ancient layers contain requires laboratory analysis of returned samples. Chang'e 6's returned samples are currently the first far-side regolith material in any laboratory on Earth. Scientists are applying the full range of modern analytical techniques to material that has sat undisturbed since before complex life appeared on Earth. Early analysis is ongoing. What those samples reveal over the next few years will define the scientific agenda for far-side surface missions through the rest of the decade and beyond. But perhaps the most striking implication of studying ancient regolith goes back to the question raised earlier about Earth material preserved on the Moon. If Earth rocks blasted to the Moon during heavy bombardment landed on the far side and got buried in regolith over billions of years, those fragments may now sit millimeters to centimeters deep in the ancient highland soil, waiting for a drill or a scoop to find them. A piece of early Earth, possibly carrying evidence of the earliest chemistry of life's precursors, sitting in the dust on the far side of the Moon, waiting. The idea stops being poetic when you realize that the samples already collected by Chang'e 6 are being searched right now, with techniques sensitive enough to identify material from another world. What happens when the next mission goes deeper, targets a specific site, and returns material from layers old enough to date back to the heavy bombardment? The answer to that question may reshape not just lunar science, but the entire story of life's origin on Earth. Scientists know roughly how old the Moon is, about 4.5 billion years, formed shortly after the solar system itself. That broad age is confirmed through multiple dating methods applied to Apollo samples. But the specific ages of features on the far side have been far harder to pin down. Crater counting is the standard method for dating planetary surfaces without samples. More craters per square mile means older terrain. The relationship between crater density and surface age is calibrated using surfaces where the age is independently known. Apollo landing sites provided the calibration points, linking crater density to known sample ages from radiometric dating. The problem is that all the calibration points are on the near side. Scientists apply the near side calibration to estimate far side ages. The assumption is that the crater forming impact rate was the same across the entire Moon at any given time, which is physically reasonable, given that impactors come from all directions. But the calibration is still an extrapolation. Far side terrain ages estimated from crater counting carry larger uncertainties than near side ages. For the ancient highland terrain that dominates the far side, this uncertainty is especially significant. The highlands are saturated with craters, meaning new impacts overlay old ones completely, making the surface appear to have reached a maximum density equilibrium rather than continuing to accumulate distinguishable new craters. Saturated terrain is extremely difficult to date precisely. The physical record of the Moon's early bombardment history, one of the most important questions in solar system science, is most clearly preserved on the far side, and the far side's ages are the least well determined. Chang'e 6 samples will provide the first radiometric ages from a specific far side location. Radiometric dating uses the known decay rates of radioactive elements locked inside rock crystals to measure time elapsed since the rock last solidified or was significantly heated. The precision achievable with modern laboratory instruments can date lunar rocks to within a few tens of millions of years, small compared to the total lunar age. Those precise ages from a known location on the basin floor, combined with the crater density observed at and around the landing site, will calibrate the crater counting method for at least one far side environment. It will reduce the uncertainty in age estimates for surrounding terrain. Multiple sample return missions from different far side locations would extend this calibration across the hemisphere. Each new sample return from a dated site tightens the age model and improves estimates for terrain between the sampling points. The payoff from this calibration exercise extends far beyond the Moon. The same crater counting method is applied to date surfaces on Mars, Mercury, the asteroids, and the moons of the outer solar system. Improving the lunar calibration improves the age estimates for every other body where direct samples are unavailable. Better age estimates mean better understanding of when geological and geochemical events occurred across the solar system, which feeds directly into models of how the solar system evolved, how often catastrophic impacts occurred, and how reliably habitable environments could have persisted on early Mars or other worlds. The far side's age uncertainty is not a narrow technical problem. Getting it right has cascading effects across planetary science, and getting it right requires a sample return campaign that is only now in its earliest stages. The science agenda, stretching ahead from the far side, is not measured in years. It is measured in generations of missions and discoveries. What those generations will find depends partly on the technology brought to bear, and partly on what the far side continues to reveal as exploration deepens. Every chapter of this story so far has introduced a discovery that raised more questions than it answered. The final chapters of what the far side can teach us are still being written, but the framework of those chapters is already visible in the science done so far. The moon gets hit regularly. Thousands of small impacts occur on the lunar surface each year, detectable as flashes of light through telescopes on Earth. Most are tiny, producing craters only inches to feet wide. Occasionally, larger objects arrive and leave craters spanning hundreds of feet. The moon serves as a natural record of the impact history of the inner solar system. Every crater on the surface is a data point about the population of objects crossing through the region of space near Earth. The size, frequency distribution of craters, how many large versus small, follows predictable statistical patterns that tell scientists about the sizes and types of objects that were present at different periods. The far side, undisturbed by volcanic resurfacing, preserves the most complete crater record available. The ancient highland crust on the far side has accumulated craters for 4.5 billion years without interruption. It is the most intact archive of inner solar system impact history in existence. Scientists studying planetary defense, the effort to identify and potentially redirect asteroids that might strike Earth, need accurate models of the impact flux in the inner solar system. How many objects of various sizes are out there? How often do they hit? How has that rate changed over time? The far side crater record answers these questions across geological timescales. Crater size distributions measured from orbital imagery, combined with radiometric ages from returned samples, translate directly into impact rates at specific periods in solar system history. Confirmed through orbital surveys, the far side highlands provide the most complete crater size frequency distribution data available for the ancient bombardment period. These data are used in current planetary defense models. But the far side offers something additional for planetary defense that is less often discussed: a telescope located on the far side's surface, scanning the sky in the radio-quiet environment. Discussed in Chapter 23, would also have an unobstructed view of a region of space that Earth-based telescopes struggle to monitor: the sky directly in the direction of our star. Objects approaching Earth from near our star's direction are difficult to detect from Earth. Sunlight blinds optical telescopes to that region of sky during daylight hours, and the geometry means dangerous asteroids on certain orbital paths can remain undetected until relatively close approaches. A telescope near the lunar south pole, positioned to view the sun-facing inner solar system, would complement Earth's detection networks and close that blind spot. The far side's unique vantage point, its electromagnetic silence, its stable platform, and its proximity to Earth all combine to make it a genuinely useful forward position for monitoring the solar neighborhood. Future proposals for lunar surface telescopes include this application, alongside the astronomical science objectives. A single array on the far side could simultaneously serve radio cosmology, dark ages observations, and inner solar system surveillance. The moon is close enough to deploy there with current technology, yet far enough from Earth to offer a truly different perspective on the sky and on our own planet's vulnerability. As the missions multiply and the science deepens, the far side is beginning to look less like a remote unknown and more like an essential piece of humanity's extended sensing apparatus. What it has revealed so far is extraordinary. What it has yet to reveal may be the most significant scientific story of the coming century. Scattered across the moon's surface are strange bright patterns that look almost painted on. From orbit, they appear as irregular, swirling shapes, bright against the darker background of the older regolith, sometimes spreading across areas dozens of miles wide. They have no obvious geological structure. They are not raised features or crater rims. They do not correspond to any known volcanic or tectonic process. They simply sit on the surface as bright, abstract shapes, some of them strikingly beautiful in orbital photographs. They are called lunar swirls, and they remain one of the most genuinely puzzling features on the Moon's surface. Several swirls appear on the far side, with some of the most prominent examples sitting in the far side highlands. The Reiner Gamma Formation on the boundary between near and far sides is the largest and most studied example, but far side swirls exist in isolation from each other, scattered, without obvious pattern. One firmly established characteristic of lunar swirls is their association with localized magnetic anomalies. Every confirmed swirl sits above or near a region of unusually magnetized rock. The magnetic fields at these locations are weak by Earth standards, but measurable. They appear to deflect some of the incoming solar wind particles that continuously bombard the surface. That deflection is the leading explanation for the bright appearance. Solar wind particles carry energy that darkens regolith over time through a process called space weathering. Areas shielded from the solar wind by local magnetic fields weather more slowly, staying brighter than surrounding terrain. The swirl pattern traces the shape of the magnetic field above it. So the swirls are visible indicators of the underlying magnetic anomalies. But that explanation immediately raises the next question. Why are the magnetic anomalies shaped that way? Some magnetic anomalies and their associated swirls sit at the antipodal points of major impacts. As discussed in the magnetic anomaly chapter, large impacts can generate temporary amplified magnetic fields at the impact's opposite point on the Moon through the plasma shock mechanism described earlier. If rocks were cooling during that amplification event, they locked in the stronger field, producing a localized magnetic anomaly. But other swirls and their magnetic sources do not have obvious antipodal impact partners. An alternative hypothesis invokes comets. When a comet's nucleus strikes a planetary surface, it arrives with its own magnetic field carried in the magnetized plasma of the comet's coma. A comet impact could deposit a localized magnetized signature in the impact zone, creating an anomaly without requiring any antipodal mechanism. Both mechanisms may be operating in different swirl locations. Confirmed, the magnetic swirl association is real. Confirmed, both proposed mechanisms are physically plausible. The specific origin of individual swirl systems remains under investigation. Future missions carrying low-altitude magnetic sensors flying just above specific swirl locations would map the three-dimensional structure of those localized fields with enough precision to distinguish between the impact antipode origin and the comet impact origin in specific cases. The swirls are one of the most visually striking mysteries the Moon offers, and they sit at the intersection of magnetic physics, impact dynamics, solar wind interaction, and surface chemistry. Solving them requires understanding all four simultaneously. They are also a reminder that after decades of orbital observation and 12 humans walking on the near side, the Moon still holds genuine surprises. Phenomena that require entirely new physical mechanisms to explain. Features that do not fit cleanly into any current model. The far side has more of these surprises per square mile than anywhere else we can reach. And the most disorienting surprise of all waits in a discovery that challenges something fundamental about how we think the Moon formed in the first place. Inside Apollo lunar samples, scientists found tiny crystals of a mineral called zircon. Zircon is remarkable for one specific reason. It incorporates uranium into its crystal structure when it forms, but excludes lead almost completely. Because uranium decays into lead at a known rate, a zircon crystal acts as a perfect geological clock. Measure the ratio of uranium to lead inside a zircon crystal, and you can calculate precisely how long ago it crystallized. From Apollo samples, zircon crystals returned ages of up to 4.4 billion years, among the oldest material ever dated in the solar system. Those ancient zircons set a minimum age for the Moon's solid crust and became foundational data points in models of early lunar history. Here is where the puzzle begins. To crystallize zircon, you need a melt rich in certain elements, including silicon, aluminum, and the trace elements that zircon incorporates. The standard model of the lunar magma ocean predicts that this kind of chemically evolved melt, concentrated enough in the right elements to crystallize zircon, would form late in the crystallization sequence, after most of the magma ocean had solidified. The zircon-forming melts should be associated with the KREP-rich materials that concentrated on the near side. Finding abundant ancient zircon in near-side samples fits the model perfectly. But recently, scientists analyzing far-side samples and combining data from multiple studies found evidence suggesting that zircon-bearing material may be more widely distributed than the near-side concentration model predicts. If zircon-forming melts existed across a broader region of the early moon, the chemical evolution of the magma ocean was more complex, involving mixing, asymmetric convection, or compositional variations that current models do not fully capture. The far-side samples from Chang'e 6 are being analyzed specifically for zircon content and ages. Finding zircon in far-side material of specific ages would either confirm that the chemically evolved melts spread more broadly than expected, or reveal that far-side impact events scattered near-side material across the moon, or indicate that the far side had its own localized magma evolution story, distinct from the near-side narrative. Any of those three outcomes would require updating the standard lunar magma ocean model. Zircon grains from the far side would also potentially record the magnetic field that existed when they crystallized, because some minerals in zircon-bearing rock capture magnetic signatures during cooling. Far-side zircons of the right age could provide direct measurements of the ancient lunar magnetic field at specific times during the early period, before the field began to weaken. The combination of precise age dating and magnetic field recording in a single mineral sample from the far side would give scientists more information about early lunar history per gram of material than almost anything else they could collect. Scientists analyzing Chang'e 6 samples are working now. The results will arrive in published papers over the coming years. Each result will either reinforce the current model, require a modification of it, or demand something more radical. The moon's story is being rewritten incrementally, one analytical result at a time, and the rewriting is accelerating. Heat tells time on planetary bodies. As a planet or moon cools from its initial molten state, the rate of cooling is controlled by its size, its composition, its internal heat sources, and how efficiently it conducts and radiates heat. Scientists build thermal evolution models that track how the interior temperature changes over billions of years. Those models make specific predictions about when volcanism ends, when the core solidifies, when tectonic activity ceases. For the moon, the thermal history models built on Apollo-era data predicted a relatively straightforward cooling sequence. Interior heat production dominated by radioactive decay declining over time, volcanism ending around 3 billion years ago as the interior cooled below the melting point of basalt at accessible depths, core solidification happening gradually over a broad time window. A moon that was largely thermally dead by the time complex life appeared on Earth. The far side has challenged that narrative repeatedly. The young volcanic deposits of only 100 million years old, discussed in Chapter 22, indicate heat persisting in specific regions far later than standard models predict. The unexpectedly high heat flow signal, detected beneath the von Karman crater floor, discussed in Chapter 6, suggests localized thermal anomalies still operating today. The evidence for a potentially asymmetric core, discussed in Chapter 16, implies the interior cooled unevenly in ways that complicate simple spherically symmetric cooling models. Taken individually, each anomaly might be explained away as a local effect or a measurement artifact. Taken together, they point toward a moon whose thermal history is significantly more complex and regionally varied than previously modeled. A confirmed finding from seismic data: the moon's deep interior retains a partially molten layer surrounding the core, the mantle transition zone referenced in the core chapter. This layer has not completely solidified. Heat from the core, residual radioactive decay, and possibly tidal heating from Earth collectively maintain this partially molten zone. If the partially molten zone is thicker or more laterally variable beneath the far side than beneath the near side, and there are reasons from the asymmetric cooling models to expect this, then the thermal structure of the moon today is genuinely three-dimensional, in a way that changes predictions about everything from future volcanic potential to the long-term stability of ice deposits. Mapping the moon's interior thermal structure in 3 dimensions requires seismometers and heat flow probes at multiple locations across both hemispheres, with enough stations to detect and localize deep seismic sources, and enough measurement duration to sample rare deep moonquake events that carry information from the deepest interior. That measurement campaign would take years to execute and requires a level of surface infrastructure not yet deployed. The science return would be transformative. For the far side specifically, placing instruments where no seismometer has ever recorded a moonquake would reveal whether the far side's seismic character differs from the near side, whether deep moonquakes originate preferentially in certain regions, and whether the far side's thicker crust transmits seismic energy differently in ways that reflect its distinct geological history. The thermal history of the moon is not a closed chapter. It is a question being reopened by every new measurement the far side provides. And as that question reopens, it connects directly to the final and most provocative question the far side raises. A question about how unique our situation is, about whether the sequence of events that produced a large moon, a stable Earth, and eventually a species capable of wondering about all of this is common or catastrophically rare in the universe. The giant impact that formed the moon required a Mars-sized object to hit the young Earth at the right angle, at the right speed, at the right time in Earth's formation, to produce a moon large enough to stabilize Earth's axis, drive meaningful tides, and set the day length to a value compatible with life as we know it. How often does that happen? Simulations of planetary formation show that giant impacts are common. Rocky planets form through collisions, accumulating mass through a chaotic sequence of mergers. But producing a moon the right size to do what ours does requires a specific subset of those collisions. A large impactor at the right stage of the host planet's growth, with a geometry that ejects the right amount of material into orbit. Estimates vary widely. Some simulations suggest that only a small fraction of Earth-like planets in habitable zones form large moons through giant impacts. Others suggest the outcome is more common than the pessimistic estimates. The honest answer is that scientists do not yet know the actual frequency. What the far side of the moon contributes to this question is physical evidence about the giant impact itself. The composition of the exposed mantle material, the thickness of the far side crust, the chemistry of the ancient highland rock. All of these carry information about the conditions of the original impact event, better constraints on what Theia was like, how the impact proceeded, and how the moon's interior evolved afterward, tighten the models used to estimate how often Earth-like outcomes occur elsewhere. The second moon hypothesis, if confirmed by far side sample analysis, would add another layer. An Earth-Moon system that formed with two moons and then merged them implies a specific dynamical sequence that simulations of planet formation can test and count. How often do binary moon systems form and merge? Does the merging improve or reduce the habitability outcomes for the host planet? Does a merged binary moon produce a more chemically complex world than a single object moon would? These questions are currently theoretical because the moon is the only detailed example we have. Every piece of information about the moon's formation and structure is a calibration point for models trying to assess habitability elsewhere. Here is the disorienting part of this calculation. If the moon's formation required a specific set of coincidences, and those coincidences also produced a moon that was necessary for life as it actually developed on Earth, then the chain of events from giant impact to complex life to a species studying the far side of the moon is longer and more contingent than it superficially appears. Each link in that chain could have been different. Theia could have been larger or smaller. The impact angle could have been different. The resulting moon could have been farther or closer. The tidal zone chemistry might not have worked. The axis might have wandered. Complex life might never have emerged. The far side of the moon carries the physical record of the earliest link in that chain, and scientists studying its ancient crust are, in some sense, reading the origin story of everything that followed. The final chapter of what the far side has already revealed, and what it will reveal in the coming years, takes all of this and asks the question that every exploration story eventually arrives at: what comes next? And what will finding the answer mean for us? We started with a wall of darkness, a hemisphere that had faced away from us for all of human history, locked by gravity, silent, unseen, generating questions simply by existing as a place we could not go. Then a spacecraft crossed that wall, and everything it found there turned out to be a mirror, reflecting our own origin story back at us from an angle we had never seen. The far side's thick crust carries the ghost of a second moon that may have merged with ours billions of years ago. The crater at the bottom of the solar system's deepest scar holds minerals from inside the moon's own mantle, minerals that tell us the moon cooled differently than the models predicted. Beneath that crater floor, a buried metallic mass the size of a small country sits frozen in the mantle, possibly the core of the object that caused the biggest impact in solar system history. Magnetic rocks scattered across the highland surface carry frozen records of a field that should no longer exist, generated by an asymmetric core that cooled one side faster than the other. Permanently shadowed craters at the poles contain ice that has not been touched by light in billions of years, brought there by comets from the outer solar system, preserved as a resource that could fuel humanity's next chapter. Lava tubes wide enough to hold entire city blocks run beneath the surface, offering natural radiation shielding, stable temperatures, and protected environments that represent the most practical habitat option we have yet identified anywhere beyond Earth. A relay satellite sitting at a gravitational balance point behind the moon bridges the silence, making it possible for humans to communicate with a surface that faces away from everything familiar. And in the electromagnetic silence behind the moon, a future telescope could hear radio signals from before the first star ever turned on, looking back through time to the very beginning of structure in the universe. Every one of these discoveries connects back to the same event, a collision 4.5 billion years ago. An impact so violent that it reshaped a planet, created a moon set the length of our days, drove the tides, stabilized the axis, and may have provided the conditions necessary for the chemistry of life to take hold on the world. That impact rebuilt. The far side held all of this, silent and unknown, for the entire span of human existence. We looked at the moon every night for thousands of years, and saw only one face. The other face was carrying answers to questions we had barely learned to ask. There will be more missions, more landers, more samples returned and analyzed in laboratories here on Earth, more seismometers recording the interior, more heat flow probes, more radio receivers listening in the quiet. Each mission will peel back another layer, but here is what the far side has already proven beyond any scientific doubt. The universe rewards going to the places nobody has been. The answers waiting there are never the ones you expected. And the moon, the world closest to us, the one we mapped and photographed and walked on half a century ago, is still hiding things that will take generations to fully understand. The impossible place turned out to be the most important place we could have gone, and we have barely started.